I think it has started recording. Okay, so right, so here is where I'll scribble my things. Okay, so draw. Okay, now I actually mentioned to you about this very important quantity, specific intensity, which is a function of space, direction, frequency, and time in general. So this is sort of like a 6-dimensional phase space distribution function. Okay, and basically what it stands for is, if dE is the energy crossing per unit area per unit time through some small area dA, dE is equal to the specific intensity multiplied by the perpendicular area times the solid angle times the time dt and frequency range d nu. Okay, so this is you have to become familiar with this quantity, because this is the fundamental quantity in radiative transfer. Okay, so basically radiative transfer is the study of macroscopic interaction between radiation and matter. Okay, okay, so we will get started. Okay, so we will actually now get to the something called the moments of the specific intensity. So moments of I nu. Okay, so what do I mean by moments? Basically what I'm saying is I will integrate over all the angles. Okay, so let me actually briefly mention again. So specific intensity is actually defined relative to actually two areas in a sense. So if this is the normal, surface normal to this, and this is sorry, not n prime, n hat, and this is n prime hat, right? So how much is that? So this is some sort of an emitter and this is some sort of a receiver of radiation. So let me just mark radiation in color. So at every point of this emitter, actually this is an important thing I wanted to mention, that every point in this emitter actually emits in broad directions, right? So basically at this point you don't only have rays going in this direction but also in that direction and that direction. So there is, every point on the emitter emits in all directions, and so this is actually important. So that means that the beam is uncollimated. So there was in the homework session that we had, there was a question about this lens, about this prism and light scattering through the prism. So I mean, normally when we talk about this prism problem, we are taking a collimated beam. Okay, so the red sort of gets bent like this, and blue in the same beam sort of gets bent like this. When you have an uncollimated beam, you're assuming that photons here do not have like a single direction. There is a broad range. So for that question, one has to actually be careful. I mean, for that sort of situation, specific intensity is not typically used, because it's assuming that at every point in the beam there are photons going in like a range of directions. Okay, so this is actually important. So how do what is meant by uncollimated beam? For example, how is it produced? For example, if you look at the photons coming from the sun, right? So if this is the sun, right? So every point on the surface of the sun, emits photons in all directions, right? So if you have like a telescope here, it receives photons, from this point, and from all the points basically, and in all directions. So this is not, so basically in this telescopic area at a given point you have photons going in all directions. So this is not collimated. So I nu is typically used in such situations. On the other hand, if you have say a laser pointer or a point source of radiation, right, you have rays going like this, right? So if you have a detector here, only you have, if you consider this point, you only have one ray direction. Are you understanding what I'm saying? So, hello?
Yes, sir.
So if you decide a point on a receiver, for example, from a point source, okay, that point does not, light from that point does not go in all directions, right? It only goes in this straight line. That is not the situation we are describing here with INU, okay? So uncollimated is important. The other thing is, I mean, it's a resolved source, not a point source. Okay, so you have to be actually careful about this point, that every point, every area, a point on every area emits in all directions. So that's how you create a beam. And now you have these two areas, and so this, okay, sorry, going back to a different color. So you have, sorry, my straight lines are not quite straight. So this is the solid angle. Uh, uh, so this flux intensity is at a given position along a given direction. So it in some way depends on both this source area, emitter area, and on the area of the detector. Right, so that's, so the detector thing comes in play because there is a solid angle in the definition. So so dE, right, the energy received, energy crossing per unit area per unit time, or crossing in time dt. So this is I nu times dt dA d omega d nu. And so if this angle is angle theta between the area and the solid angle subtended by the detector, there's a cos theta here. Now this solid angle is nothing but, if this has an area dA2, the detector has a, this is nothing but dA2 by d square, where d is this distance. Right, where d is this distance between the two, the emitter and the observer, dA2, and this, if this angle is theta prime, right? So solid angle is perpendicular area, so there will be a cos theta prime. Okay, so this is nothing but I nu dt dA d nu. Sorry, let me erase this dA. I nu dt d nu times dA1 dA2 cos theta prime divided by d square. Right, so this is just, I have plugged in the definitions of solid angle and so on. So you can actually see the symmetry with respect to the two areas, dA1, dA2, the cosine angles between the direction of the ray or the beam with respect to the two areas, right? What it means is that if instead of A2 being a receiver, if A2 was a source, right? And if the same amount of energy was, or in other words, if A2 just reflected the photons coming at that position, then the intensity measured at area A1 would actually be the same. right? Because this is a symmetric factor. Okay, so this is sort of some sort of a reciprocity between the emitter and the detector, and it's important to appreciate this. Okay, so now this is clear, right? That why do we need uncollimated, incoherent light source? And every point on the source has to have photons going in, a range of directions, not in a single direction, because otherwise, this omega and area are not independent. In this case, if you have like a area and if you have a point source, all the photons which pass this point are only going in this direction. So the area and the solid angle are not independent. Is this point clear? So this lens, this prism question, sort of to answer this is a little subtle, right? If you consider, if you don't have collimated rays, then I nu is of course constant. But if you have a collimated ray of light, what would happen is the red and blue get split. So here the I nu measured in blue is something, but if you measure I nu here in blue, it will be 0 because they have been sort of dispersed in angle. But this is not where the idea of specific intensity is valid, right? In fact, you should consider blues and reds to have a broad distribution in angles, and in that case, I nu will be constant. It's a subtle point, but an important one. Okay, so now we will go to the moments of the distribution function, unless you have a question here.
Sir,
yes.
So for what you said, when the symmetry of this definition of I nu,
Yes.
there is the dA2 part reflect back the photons. Then
Yes.
we have to assume that dA also, when it emits the photon, it also emits with the specific intensity I nu, because if it doesn't, then that will not
I
be
mean,
valid.
I'm saying all the photons that come just are retraced, right? In that
Yeah.
case, I nu is the same, right?
Yes.
Okay, so the other thing that we'll actually do in a bit is that I nu is a constant along the beam, right? And in fact, that's actually easy to see from here, but we'll come to this a little bit after we do the moments of I nu. Okay.
Okay.
So let's do the moments. So there is the first moment. So let's see. This is called net flux. This is the first moment of I nu. Right. Net flux is what is the amount of energy crossing per unit time, per unit area, per unit frequency. And this is actually represented by F nu, right? So this is energy crossing per unit time, per unit frequency, per unit area, right? Through some surface dA. Okay, so you have some surface dA, and it has some n hat, the area normal. Now you are interested in how much energy crosses it per unit time, per unit frequency, per unit area, but along all the directions, right? It need not go in one specific direction. So you consider all the possible directions of the photons, right? So what does that mean? This is nothing but, if you recall the definition of I nu, this is I nu times cos theta d omega, right? This is nothing but that by the definition of I nu. But now you are actually integrating over all solid angles. Basically, you're integrating over all solid angles. So this is a surface. So this is like this is like a variable. So theta changes for all directions. So theta goes from 0 to pi, right? So 0 to pi, and the angle covers the whole solid angle, right? So you can use like spherical coordinates, right? So this is like your n hat is like your z-axis, right? And you consider spherical coordinates around it, and this is like so this angle between z hat and r hat is like theta, and then you have phi, right? So that's why we have this. This is the definition of net flux. Okay. Now, if you have isotropic radiation, if I nu is the same along all directions, right? So isotropic radiation, what it means is that I nu is independent of angle theta. It's independent of angle theta. So what happens in that case is I nu can just come out of that integral, right? It does not depend on theta. So when we consider spherical coordinates, right, this is very important to notice. So d omega, when written in terms of spherical coordinates, is just sine theta d theta d phi, right? This is your solid angle. Why is that? Because if you recall, right, r sine theta d phi times r d theta, right? This is your area, the transverse area. This is equal to dA perp. And when you consider your spherical coordinates, r square sine theta d phi is your transverse area, right? Because this is your, sorry, I think I can, yeah. My drawing is understandable, right?
Yes, sir.
Because I don't want to like use too sophisticated drawing tools because I'm not used to them and it may take some time. So this is like your z-axis, and these are your spherical coordinates. So this is your spherical radius r. This is like, this is angle theta. This is r sine theta, right? So the line element along the phi direction is r sine theta d phi, right? This is like dl phi, right? The length in the phi direction, right? That's clear. R d theta is the length in the theta hat direction. This is dl theta. So these are both transverse to the r hat direction. So this is like area, a perpendicular area. And perpendicular area divided by distance square is nothing but that. So solid angle is given by that if you use spherical coordinates. Okay, if we assume the radiation to be isotropic, generally radiation does not depend on the angle phi, right? It's axisymmetric, but it can actually depend on angle theta. Okay, it can in principle also depend on the angle phi. If you look in terms of the spherical coordinates aligned with this area normal n hat. Okay, so but if I nu is independent of theta and phi, what happens is just this integral. So this integral f nu is equal to what? If I nu comes out of that integral, what is f nu? 0?
0.
Right, because I nu now becomes I, a constant. It comes out of this integral. This is cos theta, and d omega is nothing but sine theta d theta d phi, and of course d phi is axisymmetric, so this just integrates to 2 pi, right? And theta, the whole solid angle is covered when you go from 0 to pi, right? This is just standard spherical coordinates. So this is just so if we do a change of variable, t equals cos theta, and so this becomes so this becomes d minus cos theta, sorry. In fact, this is a good change of variable, because then dt equals sine theta d theta, right? So d minus cos theta is sine theta d theta, and it becomes so sine theta d theta is dt. This is, so basically this becomes I times so cos 0 is 1, so minus 1 to plus 1, t goes from, so t dt, and there is a minus sign. Anyway, this is an odd function. This is an odd function, and integral is from -1 to 1, so this is 0. And it's also obvious, right? What physically it means is that if you consider an area, right, you have radiation going in this direction and in this direction. Basically you have radiation going in all directions. So sometimes this cos theta adds with positive sign, sometimes with negative sign, and they all cancel. So if you have isotropic radiation, flux is 0, right? Now, the flux received at Earth from the sun is not 0, of course, because the sun is not isotropic relative to the Earth, right? There is a specific region in the sky where the sun is located, right? But if you have like the CMB, right? CMB, cosmic microwave background, is isotropic. So flux due to the CMB at any point is 0, because there is equal amount of photons going in all directions. Is this clear? This is the first moment. So this is called first moment because cos theta has first power, cos theta to the power of 1. Okay, now, so this is the first moment. And the idea is this is just the energy crossing per unit area, per unit time, per unit frequency. All these quantities which have nu as a subscript, we can always integrate them over and obtain a flux which is integrated over frequency. So you can get F, you can define a flux is equal to F nu d nu. Basically, you integrate over all frequencies. Now, what are the units of F nu? The units of F nu would be erg per second per hertz per centimeter square, right? And and the units of F would be erg per second per centimeter square, of course, because you have integrated over frequency. So when we typically ask, the sun has this much luminosity, calculate the flux, this is what we are actually calculating, right? Okay. Okay. Right. So basically, you're integrating over all solid angles. Okay. Now, what about the second moment? The second moment is radiation pressure or momentum flux. Momentum flux. Flux of momentum of the radiation. Okay, so let me create a little space. You are all able to see what I'm writing, right?
Yes, sir.
Yes, sir.
It's legible and understandable?
Yes, sir.
Yes.
Okay. Yeah, you can interrupt me if something is not clear. Okay, momentum flux. Okay, now let's consider an area, right? And this is your area normal n hat, and some angle theta. This is the direction of the ray that we are, of the light ray that we are considering. Okay, so dE, the amount of energy going along this omega hat is is equal to I nu times d omega dA cos theta dt d nu, right? So this is the amount of energy that crosses this area per unit time, per unit frequency, per unit solid angle along this direction omega hat, right? So this cos theta factor is important because if this area was aligned perpendicular to the direction of the photons, there will be no energy crossing it, right? So this cos theta is important, and a lot of times students do mistake in this. Right. Okay. So this is the energy crossing along this direction. Now we know that the photon has a momentum which is just given by E by C, right? Because the photon is a massless particle, and this is equal to E is h nu for a given photon with frequency nu. This is h nu by C. Okay. All of you know this, right? For a massless particle, momentum is E by C. Is there anyone in the class who does not know this or has not encountered this before? Okay, good. I think, yeah, this is basic enough that everyone should have seen it in one of their previous courses. Okay, so this is the energy crossing along this direction. What about the momentum crossing along that direction? So the momentum along omega hat corresponding to this energy is equal to just dE divided by C, right? Because every photon just carries momentum E by C, so all these photons will have, having range nu to nu plus d nu, and their numbers sort of quantified by I nu will have a momentum along omega hat of that amount. What about momentum along n hat? Oops, along n hat, right? N hat is this area that we are considering, this perpendicular to this area. So this will be nothing but momentum along this direction times cos theta, right? So that would be dE cos theta divided by C, right? And if we plug that in, the expression for dE from above, that just becomes I nu by C. Oh my God, why is writing not I nu by C times d omega dA dt d nu times cos square theta. Okay, now this is the momentum along n hat due to photons which pass at an angle theta. Okay, but we are interested in adding over all such photons covering all these angles theta. So what happens? So that is basically, that's what the pressure is. Pressure so this is pressure, radiation pressure. Okay, P nu is equal to, basically you integrate over all these angles theta. That is nothing but so this is just flux of momentum, right? So this is sort of momentum flux, and that's nothing but the above expression. So for flux of momentum, or which is nothing but momentum along n hat divided by per unit time, per unit area, per unit frequency. That's the flux, right? Flux is per unit area, per unit time, per unit frequency. If you're interested in P nu, you can integrate over nu and get P. Like we went from F nu to F. So when we do this integral, so what does it mean? So this is just I nu. So 1 by c comes out of this integral. This is I nu cos square theta d omega, right? So this is called radiation pressure. Radiation. Okay. Right. So even in if you do a little bit of kinetic theory, right? Pressure is not. I mean, pressure is nothing but the flux of random momentum, right? So pressure is nothing but flux of momentum. So this is one way of looking at pressure from the kinetic theory viewpoint. Normally we think of pressure as force per unit area. That's another way of looking at it, but they are one and the same thing. Okay, flux of momentum. Do you understand what I'm trying to say? Like this flux of momentum interpretation of pressure, you encounter this in kinetic theory. When you go, when you have the distribution function and you take the moments of the distribution function in almost the same way that we did here. The second moment of the distribution function is pressure for the gas. Here we are taking the second moment relative to the angle in almost the same sort of way. So this is radiation pressure. Now you see because of this cos squared theta, this quantity is positive definite. So pressure will always be, non-zero, non-negative, sorry. Right? It will either be 0 if there is no I nu, or greater than 0, as it should be. So this has the correct interpretation of pressure. Okay. And as I mentioned previously, you can always integrate over nu, so you can get radiation pressure. That's nothing but P nu d nu. That's sort of trivial part of it. So this is the pressure, and you can actually take the third moment and whatnot. So you can do cos cube theta d omega and so on. Right now here. We are actually defining these quantities with respect to some area, right? But these quantities have independent existence. They really don't need an area to be defined, just like gas pressure, right? Normally when we introduce gas pressure, we say that, oh, it's the force per unit area, right? In the same way here we have introduced a surface, but momentum flux P nu is actually a tensor if you think about it, and similarly the flux F nu is actually a vector, right? Because let's go up. So this right, so this F nu, this cos theta, right? If we don't, if you don't consider this area, so F nu is nothing but, so let me just write here, F nu, if you write it as a vector, is nothing but integral I nu n hat d omega over all solid angles, right? If I take a moment of this, if I take like a component of this vector along some direction, n hat just becomes cos theta, right? But this is like a more mathematically precise definition of flux. Flux is a vector, I nu n hat d omega, and n hat of course changes with the solid, the ray that you're considering. So these expressions are sort of one and the same thing, except that here I have written it in a vector form, right? In the same way, pressure is actually a tensor, and that's nothing but, in analogy to this, it's nothing but this integral over all solid angles I nu n hat d omega, right? And you can actually see why this cross square theta comes. If I take its components along some direction, so n hat dot that direction gives me cos theta. Okay, so this is just an aside, but an important one. So if someone really goes into radiative transfer, then you have to deal with all these mathematical aspects of it. Okay. Okay, so this is momentum flux. So another important related quantity is something called radiation energy density. What is radiation energy density? Basically, as the name suggests, how much energy is stored in radiation per unit volume, right? So that's radiation energy density. So let's see. So this is energy stored in radiation per unit volume per unit solid angle. So per unit volume per unit solid angle per unit frequency. Frequency. This is called U nu.
Sir.
Yes.
Okay. No.
Yes, go ahead, please. What's your name? First tell your name and then ask question, please.
Sir, this is Kinjal, but I don't think it's a function of omega. It's just dE dV d nu.
Right. So no. You can actually define it as a function of omega, and then you can average over omega, just like what we did previously.
Okay.
Okay.
Yeah, sure.
So the more this is actually more fundamental in some sense. Okay. So let me yeah. So basically, if you consider, say, some area, okay, and you have, this is again your n hat, and if you consider some photons sort of going along some direction theta with respect to it, okay, all these photons in time dt, right, in time dt will sort of, this photon beam going along direction omega hat, this is omega hat, right? So this will, in time dt, this is the path length of photons, so c times dt, right? They are moving freely, so they are moving at c, they cross a distance c dt, and this angle is angle theta again. Now, right, so this is energy crossing this volume per unit solid angle, right? So this is only considering photons going in this particular direction, not in any other direction at this point. Okay, so how much is this energy? So dE, okay, is what? In terms of specific intensity, we know that the energy crossing per unit time along that direction omega hat is I nu times dt times dA times d omega, okay, what, so d nu, right? So this is the energy and cos theta, of course, the very important factor of cos theta, right? Because this area is not perpendicular to the direction of the photons that we are considering. So this is the energy crossing this this area along that direction. Okay. Now, right. So if we multiply and divide this by c, right? So now this c dt, right, so this factor, what is this? This is c dt times dA, this is the area of this surface, cos theta. This is nothing but the volume, right? This is nothing but the volume of this cylinder in which photons just travel in time dt, right? So energy, oops, just a sec. So the energy crossing per unit volume, per unit time, per unit frequency, per unit solid angle, per unit volume is concerned, sorry, not this, per unit solid angle, yes. Solid angle is equal to, because, solid angle is not covered yet, right? Because you're considering only photons going in a particular direction. So that is nothing but u nu. And that is given by I nu divided by C omega d nu. Oh, sorry, dt is gone, right? Dt is absorbed in that. So let me erase that. So this dt is not going to be there, right? Because that C dt is part of dV, right? So u nu is equal to I nu by C, right? So this is the relationship between energy density of photons traveling in certain direction and the specific intensity, right? So this is actually very reminiscent, if you recall, of E equals P by C. E equals PC. So this is like energy, and that's like it's energy per unit volume, and that's sort of like a momentum flux. Let me actually not talk about this now. It's a little confusing. I'll come to this later. Oops. Okay. So U nu equals I nu by C, and of course the units of this are erg per centimeter cube. No, just a sec. And the units are erg per centimeter cube per hertz per steradian. Okay. Okay, so this is U nu. U nu as a function of omega, right? So this is U nu as a function of omega. What you can actually do is you can integrate over all solid angles. Then you can actually get U nu. This is integrated. I mean, see, a lot of times you have to pay attention to the units, right? If you have per steradian, that means it's per unit solid angle. If it does not have per steradian, that means it's just erg per centimeter cube per hertz. U nu is equal to U nu omega times the omega. So you integrate over all solid angles. Just a sec, let me create a little more space. This is nothing but 1 by C times I nu d omega. Okay. So this is nothing but this looks like a this is related to the 0th moment, right? Why am I calling this the 0th moment of I nu? Can someone answer this?
Because sir, 0th component on momentum is certainly related to energy.
In terms of like, yes, it is cos theta to the power of 0 here, right? You can think of this as 1, and 1 is nothing but cos theta to the power of 0, right? We had flux, which was cos theta to the power of 1. We had pressure, which is cos theta to the power of 2. And this is just I nu d nu. You're just adding up all the I nus along all different solid angles. So this is called the 0th moment. Okay. So this is there is something else which is also very related. This is called mean intensity. In this, in radiative transfer, there are a lot of these terms that are introduced, and it's important to actually pay attention to what actually they are, right? The main difficulty is just sort of paying attention to the definition. Once that is clear, things are pretty straightforward. So mean intensity, which is represented by capital J nu, is nothing but 1 by 4 pi integral I nu d omega, right? So this is like an average. So angle averaged intensity, right? You're basically taking the intensity and you're averaging it in all the different angles. 4 pi is the total solid angle, and you're just sort of adding up I nu along all the directions, and angle. This is basically angle average intensity. This is called mean intensity. So you can actually see that this object, which is U nu, radiation energy density, is actually closely related to this. So U nu is nothing but 4 pi J nu divided by C. So you see this radiation energy density has the same dimensions as pressure. If you go up, you will see the pressure was, dimensionally it had this extra cos square theta, but in terms of the units, this is nothing but I nu by C. Similarly, U nu is I nu by C in terms of the dimensions. So it's, pressure and radiation energy density have the same units. Radiation, similarly to the gas pressure and the gas energy density have the same dimensions, right? Just a sec. It is okay. Just a sec. Okay. Okay. Again, you can actually integrate U nu over all frequencies, and you get U, which is energy density, which is nothing but integral U nu d nu. Okay. So here again, as I mentioned, that a lot of complication is due to the definition and nothing else. Huh? Okay, so this is mean intensity. Now, so we also define radiation pressure, but suppose you go to a traditional way of talking about pressure. Suppose you have an enclosure, okay, and you have isotropic source of photons. So you have photons hitting this enclosure, uh, at all points. So suppose you consider this point, you have a photon which hits it here. This is some angle theta, right? It hits it and it gets reflected, right? So these angles are equal. If you consider such a situation, what is the pressure exerted at this surface where the photon is hitting? It's nothing but P nu is equal to 2. Let me just first write and then explain. So 2 by C integral I nu cos square theta d omega. Okay, what I've done is I've just sort of asked, so a photon will hit it and gets reflected. So, right, so like the considerations that we had previously when we were considering the flux of momentum, there are two powers of cos theta. One, due to the fact that the flux and the area have this cos theta factor, and the other cos theta comes because the momentum, we are considering momentum normal to the surface, so you have to take that cos theta. So this is again, and this factor of 2 comes because we are considering a reflection of the photons at the surface. Okay, but in this case, what is the range of omegas that we are considering? Yeah, you won't have photons coming from, theta can only go from 0 to pi by 2 in this case, right? For 0 greater than pi by 2, there are no photons which can get reflected from the surface, right? Only the incoming photons at this surface can get reflected. If a photon is going in this direction, if a photon is going in a direction which is not towards the normal, it is not reflected. So that's why this theta goes from 0 to pi by 2 instead of 0 to pi, as in the case of, as we considered previously, we didn't consider any surface. Okay, so what is this? I mean, in the end, you get the same expression as before, and you have to get it because pressure is pressure. Pressure is independent of the surface that you consider, right? This is the same expression that we had previously. Let me go back to that. Right, so this is that expression I have written down. So this is I nu cos square theta d omega. Here, theta goes from 0 to pi. Because you are not considering any reflection, you are just considering photon momentum crossing this area in all directions. So you also consider these incoming and outgoing photons both. But we have this factor 2 here, but this reduction in solid angle by a factor of 2. But in the end, you have the same quantity that you get, because radiation pressure is radiation pressure. Right. The other way of thinking about it is this reflected photon can actually be thought of as a photon which, if this enclosure was not there, this photon would be like this photon which is coming from there, right? So since it's isotropic source, so we are considering isotropic isotropic radiation, then all these rays have the same intensity I. Okay, so if it is an isotropic source, what happens in that case? This is nothing but, oops, sorry, let me change the color. Okay. Just a second. So this is equal to right. So I knew. So I'm considering isotropic source. So I knew comes out, and you know that I knew is nothing but J nu. If I knew is a constant, this J nu and I nu are equal, because you know if you just do this integral over d omega, it's just 4 pi. So let me just call this as 2 by c J nu, which is independent of theta, and I'm also assuming, so this is nothing but cos square theta, right? So this cos square theta is actually averaged over all angles 0 to pi by 2, and the solid angle is nothing but 2 pi, right? Because you're only considering half the solid angle, you're only considering photons which are going towards the wall, right? Same, like this 2 and this 2 pi makes it 4 pi. And what is cos square theta? Average of cos square theta in spherical coordinates? 1/3. No.
1/3.
It's 1/3. See, this is not a cylindrical polar geometry, right? This is nothing but cos square theta d minus cos theta, right? Integral from you know, so this is basically t square dt, right? So say from 0 to 1. So yeah, so this two is not there, sorry. Okay. because I'm only doing an integral from theta equals I'm doing an integral for theta equals 0 to pi by 2. So cos theta goes from 0 to 1, and this is nothing but t cubed by 3, which is 1/3. Right. So right. So this is 1/3. So just a sec. Let me create a little more space. Oops. So what we have is P nu is equal to 4 pi by 3, 4 pi by 3 integral, not integral. So what I'm actually doing now is I'm actually integrating. Yes. So 4 pi by 3. So I'm actually integrating over frequency too. J nu. Oh man. Three C 4 pi by 3. You're right. So and then J nu. D nu. So I've actually integrated over nu as well. So now what I'm actually getting to is this relation between pressure and energy density, radiation energy density, right? So where did it go? Here. So this is like 1 by C. Just a second. Yeah. So U nu is this U. Okay. So this is your U nu. And this is your P nu, which I have actually integrated over nu. So this integral over d nu is trivial. So this is nothing but pressure is nothing but 1/3 of energy density. This, of course, we know from thermodynamics, right? Pressure and energy density are related by this gamma factor, right? Pressure is equal to gamma minus 1 times the internal energy density, right? For gas, for example, pressure is, for an ideal monoatomic gas, 5/3 minus, so pressure is 2/3 energy density of gas. But for radiation, gamma is 4/3. So pressure is 1/3 times U. So this is the relation between pressure, energy density. This is sometimes called the equation of, why is my writing so bad? Just a sec. So pressure, energy, density. This is the relation between pressure and energy density for radiation. Okay, but this is actually important, and this can also be derived from thermodynamic considerations. Here we have derived it more from kinetic theory considerations, using the fact that pressure is the second moment of I nu, and the energy density is the 0th moment of I nu. So the second moment and the 0th moment are actually related by this. Okay. Okay, so I will. Okay, so this is good. Now, one thing that I would like to prove before I end my class today is this constancy of I nu along the way. So basically, specific intensity is constant in vacuum. If there is no no emission or absorption of radiation, then specific intensity is a constant. This is what I want to prove. Let's see. So let's consider this situation. So you have some area dA1 and some other area dA2. Okay, now let me just draw some photon paths. I consider all the photons that come from here. No, my drawing is not quite up to the mark on this. I'll try again. So, I want to connect this. Oof, it's not easy. So there are photons. As I said, when we consider these areas, at every point we have to consider photons which travel in all directions. So you will have photons, ignore the bending of these lines. They're traveling in straight lines. It's just my poor drawing. So this is, for example, one. So basically, all the photons which are crossing this and crossing this area D2 are the ones that we are considering. So the energy that is crossing area D1, dA1 and area dA2. So this is actually the distance between these areas, D. So this energy is nothing but I. So let's consider energy crossing area 1 as I nu 1 dA1 d omega 1 A1 omega 1 d nu 1 dt1, right? So this is the energy crossing area dA1 along this solid angle d omega 1. So d omega 1 is nothing but this angle subtended by area dA2, and I'm actually considering them to be, you know, collinear, these areas and the line connecting them. The area normal is along the line connecting them, but you can also consider other geometry, but you know, this, the considerations are the same. So d omega 1 is nothing but the transverse area dA2 divided by this distance square. Right, this is the definition, and since I'm considering theta equals 90 degrees, and there's no cos theta factors here. So this is the solid angle d omega 1. Now this energy dE2 that is crossing this area dA2 is nothing but same definition, actually, I nu 2 I knew. Now I know why my drawing is poor. If I try to write too fast, it just omits it. D A 2 dA2 d omega 2 d nu 2 dt 2. Okay. Now we know that, you know, in vacuum, d nu 1 and d nu 2 is the same, right? The range of photon frequencies which are crossing area A1 and crossing area A2 will be the same. Similarly, the time dt1 over which you are actually measuring these photons will be the same as time dt2, because light travels with speed c. So these quantities are equal. The other thing, we know that by energy conservation, whatever energy crosses this area at some time will cross this area per unit time in the same amount of time. So this d and dE2 are equal, d nu 1 and d nu 2 are equal, and dt1 and dt2 are equal. Okay. So if we take that equality, what we get is I nu 1 dA1 d omega 1 dA1 d omega 1 is equal to I nu 2 dA2 d omega 2, right? But we know that d omega 1 is that, and d omega 2 is equal to d A1 by d square, right? So if we substitute d omega 1, that's dA2 by d square, right? And omega 2, which is dA1 by d square. So this is nothing but this implies, right? So this dA, d omega factors cancel on both sides if we plug these expressions in there. So what it gives us is I nu is equal to constant along the beam, right? I nu is a constant along the beam, or d I nu by ds, d I nu by ds is equal to 0, or specific intensity is preserved along a ray, okay, in absence of absorption and emission and scattering along the line of propagation. Now, so this was in vacuum, but if you have like refractive material and all that, this all goes through. As long as there is no absorption, emission and scattering. In absence of these three phenomena, which we'll actually consider in more detail later, this is preserved, right? And in fact, if you have refractive elements in the middle, like here, like lenses and so on, even then this is correct, okay? So this is actually very, very important fact, that I nu is constant. Specific intensity is constant. So the rays coming from the sun, if you measure the specific intensity at the sun, and if you the specific intensity at the earth, it's the same. And it sort of looks a little non-intuitive, because if you're closer to the sun, the flux received is a lot, but the solid angle subtended by the sun is also large. So if you divide them out, so flux divided by the solid angle, it is the same number. Okay, so I think we are at the end of the class. So I'll end here and we'll start with radiative transfer, elements of basic radiative transfer from the next class. So any questions?
Sir,
Yes.
so in the last part, what you said here, the for the definition of D equal to this I nu dA d omega d nu
Yes.
dt, there the solid angle is the subtended by the area dA at the source. So
Yes.
so here the dA1 and dA2 both are acting as a source, or there is another source and we are taking that.
No. DA1 is sort of acting as a source. As I said, right, we cannot, so here when we are doing this sort of radiative transfer, we are actually assuming that every point on this area DA1 is emitting in all the different directions, right? If we consider like a single source which is unresolved, then this omega hat and this area are not independent variables. You see what I sort of paid attention to this a little bit at the beginning of the class. This angle and the area are two independent variables.
Yes.
Okay. So it's this distance d which matters, not the distance from some original source. Right.
Yes.
So for example, you know, as I said, this is actually not applicable for collimated beams or for point sources. There you have to be more careful. There you really don't need this solid angle and area to be independent. There you can just think of it as flux considerations. Okay, but when we are sort of talking about, say, radiation from the sun, this is exactly the situation that we have, right? So
but sir, we are measuring the flux, the radiation coming from the sun, we are measuring it in earth. But suppose someone is at the sun, hypothetically, so at the sun, then he will measure the radiation coming from the earth, right?
No. See, I'm not sort of right. So the rays are reversible, right? So what I'm actually saying is that you are just in this example, what you're considering are the rays that are sort of crossing these areas in given directions, right? So whatever the energy crosses this area per unit time is the same as whatever crosses this area, right? And we are just saying it's a sort of a steady state. Whatever crosses this will cross this, because we are only considering the photons which are crossing both these areas in all these
So
directions.
then these two areas have to be in some kind of a isotropic radiation thing, because then the whatever will cross DA1, that will cross DA2.
No, it need not be isotropic, right? You don't need to have like radiation going in other directions, for example, but you have to have like these areas are small enough, right? These areas are small enough that the solid angle is small. These areas are small so that you can actually consider all these points to be very, very similar, right? This is like differential area.
Yes, but the D is not small, so
DA is small. DA
no,
is small.
the distance between these
Distance
two
D is
areas.
not small.
Yes, so that may cause that the radiation which passes through DA may not pass through DA2.
Right, it will not, but we are only considering the radiation. So, what you're saying is absolutely right. You can have radiation which goes in this direction, right? And it crosses DA1 but not DA2. But we are not considering this, right? This is not part of this solid angle. This ray that I drew in green is not part of this solid angle d omega 1. I'm only considering photons going in solid angle d omega 1, right?
Okay.
So that's why, that's why this is not counted. This photon or this photon are not counted.
So it's kind of a mutual exchange.
Yes, right. So when we are defining specific intensity, actually there are two important areas. One is the area where you are crossing it. The other is the area in which you are looking at. That's the solid angle, right? This dA2 is related to the solid angle. So I nu is a function both of a given area and the solid angle. So you should keep this in mind. Okay.
Yeah. Sir, yes. Sir, another question. The thing you have written there, the relation between pressure and the energy density. There you wrote that P equal to gamma minus 1 multiplied by U. So here for the photon case, we can see that it's the gamma is we get 4 by 3. So, but we get the gamma from the kinetic theory. We get the gamma from degrees of freedom, calculating the degrees of freedom. But then photon, if you think the photon as a single particle moving in space.
No. See, this gamma 4 also comes from the kinetic theory, but these are relativistic particles. So E for a particle is equal to Pc, not P square by 2m. Right? Because of that, P square, right? So because of
some
this,
extra freedom is coming.
Yes, it's not. I mean, it's isotropic and everything. The main difference is because E equals Pc, not P square by 2m for non-relativistic particles, right? When we take like this, when we take the moments of the distribution function, this extra square versus single power gives you four in E equals Pc it gives 4/3, and E equals P square by 2m it gives 5/3. Okay.
Yes.
I can actually add this like a homework problem. Okay. Is this clear?
Sir,
Yes.
can I?
Yes.
So I mean, I saw many of the problems in the homework. I mean, they are. I mean, it's not that we can do it right now, right? I mean,
No, you
most of.
cannot.
Yeah. That's what I was wanted to
Yeah,
ask
yeah,
because.
yeah. I mean, this is really like this is homework problem corresponding to chapter 1. So
Okay.
you slowly look at this material, see what you can do right now. Of course, some of these things are more, we'll do in future classes. But I want to give that right away because, you can at least start having a look at those.
Okay. Thank
And
you.
try to look at it like in our Friday sessions, we can actually go over some of them, right?
Yes.
In
Yes.
these
That would be
classes,
helpful.
we don't have as much time to really get into the nitty-gritties. There we can do that. Is the writing okay, or should I try to go to a blackboard?
Yes,
Hello.
sir. Whichever is
I mean,
convenient.
is this okay for you guys? I mean,
Yeah.
I
Yes,
am
sir.
actually,
It's fine.
it's fine. Okay. Okay, thank you. So I'll see you day after tomorrow. Bye.
Thank you, sir.
Bye. Let's end the meeting. How do I do that? Oh, okay.